Okay, this video is going to go through how to calculate the rate law and the rate constant for the reaction above. Okay, so the first thing is you'll have to have a balanced equation to see kind of what's going on. You can't really get the rate law from the balanced equation, but you can get the backbone for it at least. And so the rate law is going to be this right here. It's going to be that the rate is going to equal K times the concentration of, or rate times CO2, the concentration of that. So you put that in brackets, that means concentration, and it's not CO2, it's CO, to some power, and that's what we're going to have to determine from the data. So I'll just call that M, the variable is unknown. Okay, and that's going to be multiplied times the concentration of O2 to some power N that we don't know. Okay, remember when writing the rate law, the backbone for it, only gases and things that are aqueous are part of the rate law. Solids and liquids won't count. Don't count because they don't have a concentration. All right, so anyway, so the first thing is you have to determine it in terms of CO, carbon monoxide, and then do it for O2. So you want to look at the data table that the problem will give you, and you want to find where, to do it for CO, you want to find where the O2 is held constant. So you can see in trial, or experiment 1 and 2, they kept the O2 constant but varied the CO. So what I like to do then is just take the big number, which is 0.040. It doesn't really matter which way you do it, but I always like to take the big number over 0.020. Now that's going to be, those concentrations are going to be to some power M that we don't know yet. Now what we're going to do is see how these concentrations affected the rate. So then I'm going to put the 1.47 e to the minus 4, and I'm going to divide that by 3.68 e to the minus 5 here. Now what's really important is you want experiment 2, you got to keep it in line. This is experiment 2, so directly across from the equal sign is the experiment 2 rate, and down here is experiment 1, and this is experiment 1 rate. So if you do the math here, you get 2 to the power of M is going to equal 4. And then you got to think, well, 2 to what power equals 4? So M equals 2. So in the rate law, in respect to carbon monoxide, the order is 2. All right, now we're going to do the same thing for O2. We find where we have experiment 1 and experiment 3 is where the CO is kept constant and the O2 is varied. So once again, for O2, I'm going to take the big number, which is experiment 3, 0.040, and I'm going to divide that by experiment number 1, 0.020. Once again, I'm looking for where experiment, the CO is kept constant, but the O2 is varied, so I'm doing experiment 3, experiment 1. That's going to equal 7.36 e to the minus 5. I'm going to divide that by 3.68 e to the minus 5. Notice how I had experiment 1 here, experiment 3 here. And so then you're going to get 2 to some power n, we'll call that n. 2 to some power n is going to equal those divided by each other, which is equal to 2. So n, therefore, will equal 1. Okay, so now once we have that done, we can write the rate law, and we'll get that the rate will equal some constant K times CO to the second power times O2 to the first power. Now you could write the one there, just leave it blank, means to the first power. Okay, that's the rate law. Now the next step would be to get what the rate constant K is equal to. So you just pick a trial or an experiment. I'll just pick experiment 1, and I'm going to put in the initial rate. So the initial rate is 3.68 e to the minus 5. Okay, and the units are moles per liters per minute. Moles per liters, I like to just change that to one constant of molarity. So my units are molarity, minutes, and I like to use exponents to the -1, so which means the same as divided by minutes. So my units are molarity, minutes to the -1. Do you see that that unit right there is the same as this unit right here? All right. Now, that's going to equal K. That's what we're trying to solve for. So then we just put the concentration of CO in there for experiment 1, which is 0.020. And the units for that are moles per liter, so I'm just going to put capital M. That just makes it easier. Okay, and that's to the second power because we used the rate law that we just came up with. We're going to put that times O2 from trial 1, which is also 0.020. It's also in the units of molarity, and that's to the first power. Okay, so then if we do all this math, we get 3.68 e to the minus 5 molarity minutes to the -1 is equal to K. Let's see here, I got to remember what that number is. And let's see, that's going to be equal to 8 e to the minus 6, so it's going to be K times 8.00 e to the minus 6. And so then if you take 3.68, oh yeah, I forgot, and this is going to be the molarity to the third power, because a molarity squared times molarity to the first is equal to a molarity to the third power. So then if you take 3.68, if you divide both sides by 8 e to the minus 6, you get K is equal to 4.60, keeping the number of significant digits right. And then the thing is, you got to get the units correct. Okay, so basically the units are kind of the hard part. If you have a molarity minute to the -1 and you're dividing that by molarity to the third power, remember it's dividing exponents is like subtracting. So basically you got a 1 minus 3 gives you a -2. So the units would be molarity to the -2 minutes to the -1. That's the units that you could get for that. And that would be the answer for the rate constant right there. You could change this back into moles per liters, but I don't really think there's a need to do that, I guess, because molarity is moles per liters. Okay, that's it for this one right here. So anyway.